the beach. So they're like, I just want to have vacation for a few more days, so we're just not coming back in. All right, so starting today, we're going to start our final unit for the problem-solving stuff. Woo! Can you believe it? Last unit. I know. Where is time going? So we've got. We're going to be talking about factorial designs. Factorial designs are those experimental designs that have more than one independent variable. This is probably the most common kind of experiment that you'll find in peer-reviewed research studies. And that's because these kinds of experiments are really, really flexible, and they allow us to study phenomena that actually have or things that make a lot more sense, if you think about it, in real-world terms. For example, in just about everything that affects us, every choice we make, everything we do, is influenced by multiple factors. Different things come together in combination to cause something to happen. Like, why do car accidents happen? We know they happen every day on the connector, right? Every single day, somebody has an accident on the connector. Why? It's not the same reason every day. Sometimes it's because people were texting and driving too fast. Or maybe it's because it had been raining and the roads were really slippery, or it was icy, and they don't have a lot of driving experience. They don't know how to drive on ice, because if you don't have a lot of experience doing that, then if you hit an icy patch, you might actually turn your wheel the wrong way and you end up with a problem, right? Could be that they aren't taking good care of their tires or their brakes, and they're drunk, right? So they don't have good traction, and they're out of control because of drugs, whatever. But why does an accident happen? It's usually not a single thing that causes an accident to happen. It's usually a combination. The reason you chose the clothes you wore today to come to school, it's some combination of how much you care, right? What was clean? How much energy you had when you got up? How much time you had to get to work? Right? Who you're trying to impress? There's always a bunch of things that come together. Each one of those factors combines with other factors, and some days some factors are more important than others. And that's what factorial designs allow us to explore. How do multiple factors influence and cause behavior? Not just one, but maybe two or three, all impacting subjects at the same time. And how do those, do they work independently? Do they work together? That's what factorial designs let us explore. Now, they let us manage the challenges of experimental design in some interesting ways. Remember, number one challenge of a between subjects design is creating groups that are similar enough to compare. Managing individual differences, because the different groups we're comparing are made up of different subjects. Well, if we can use more than one independent variable in an experiment, then we might be able to take something that was an extraneous variable before, like age, and turn it into an IV and study it too. So if I'm worried, for example, maybe I'm doing a study and I'm worried that there's a lot of, diversity in the age of people in my study, and I don't know for sure that people of different ages are going to respond the same way to my treatment, well, now I can have my treatment, and I can also divide the people up by age on purpose, and have young people and middle-aged people and older people, and test them separately, but at the same time as everybody else, and look to see if age matters too, which I couldn't do if I could only look at one independent variable. This allows us to reduce variance within groups. So for example, if I take all the young people and put them together in one group, and all the middle-aged people and put them together in one group, and all the older people and put them together in one group, well, now the people in each group are more like each other, right? I'm now reducing the individual differences in each group. And I can now worry less about those differences, and that's important in a between-subject study. Within subject studies, remember our number one concern is sequence effects, right? Well now, if I can look at more than one independent variable, I can actually make sequence a variable itself. I can actually look to see if order matters and study it systematically. I can use statistics to compare order 1 to order 2 to order 3 and see if they are different from each other. And if I find that there are no statistical differences between the different orders, then I can say, look, I can demonstrate clearly there are no order effects here. It's not a problem. I also have the opportunity, which I've never had before, to do what we call mixed designs. Designs where I can have a between subjects variable and a within subjects variable, or a manipulated variable and a subject variable, or any combination of those things. So I have a lot more flexibility. I can explore how subject variables interact with manipulated variables, or how between subjects variables interact with within subjects variables, if I want to. So factorial designs give us a lot of flexibility, but they also give us power to manage challenges of single factor designs in ways that let us use statistics to show whether or not those problems are actually a concern. So for example, you guys remember this classic, right? We're comparing how many cups of food dogs eat, and we're comparing chunks and lumps, Purina 1 and Kroger kibble, right? The classic Dr. Darnell experiment. We talked about how we could do this between subjects, right? Where one group of dogs eats chunks and lumps, one group of dogs eats Purina 1, one group of dogs eats Kroger kibble. And if we did it between subjects like that, and we had lots of different kinds of dogs, we might do something like a matching procedure to make sure that we had some large dogs in every group, and some medium dogs in every group, and some small dogs in every group, right? To try and distribute those differences across the conditions as much as we could to try and minimize individual differences. If we did it as a within subjects design, then every dog would eat every food and we'd have to switch it up, right? Some dogs would eat chunks and lumps the first day and Purina 1 the next day and Kroger kibble the third day. And some dogs would eat Kroger kibble on the first day and chunks and lumps on the second day, Purina 1 on the third day, right? We'd mix it up like that. Well, imagine if we did this as a factorial. I can do something else now. I can still have cups eaten over here on the y-axis. Down here I still have the food, right? This is one of my independent variables. But now I've added another variable, and that's what's up there on the legend. So now I can actually say, well, instead of just trying to use a matching procedure or something like that to distribute different breeds of dogs across the conditions, why don't I turn breed of dog, in terms of size, into an independent variable itself? So now I'm going to have small dogs in every condition, medium dogs in every condition, large dogs in every condition, but I'm actually going to look to see how they differ. So now instead of just having a single bar for each one of those foods, I can now look and see, does it really matter what breed of dog? Well, I can see that small dogs always eat the least, right? That's still true. Medium dogs eat a medium amount. Large dogs always eat the most. None of those things are surprising. But what other pattern do I notice here? I notice that it doesn't matter what kind of dog, whether it's a small, medium, or large dog, the tallest bars are always here. The next tallest bars are always here. The next tallest bars are always here. So I can see differences that make sense. Differences that have to do with the size of the dog. But I can also see the things that they have in common, which is that they all prefer chunks and lumps, still. But I can look at those two things separately. And being able to talk about data like this is much more compelling, because I can say, we tested this with many different breeds of dogs, and what we found was a very consistent pattern. Even though, yes, different sizes of dogs did eat different amounts of food, quite consistently, all breeds of dogs, regardless of size, prefer chunks and lumps over the other brands. And I can say that not just saying, well, we distributed across and we got these averages for all of them together, which is fine. But this is a much more compelling story because I separated out breed and I can actually show how it works. Now imagine it with the within subjects. Here we've got mean number of cups, still on the y-axis, still have our foods down here. What I've done is we've got 3 possible orders that I'm presenting here. We've got chunks, Purina, Kroger, Purina, Kroger, chunks, Kroger, chunks, Purina, okay? So this is how much chunks and lumps the dogs ate, depending on which order they got the food. This is how much Purina 1 they ate, depending on which order they got the food. This is how much Kroger Kibble they ate, depending on which order they got the food. And what do you see? Does order matter? Well, how do we know? We look at this and we say, how close together are these bars? Because each one of these bars represents a different order, right? So we can see that it's not exactly the same, right? The different orders were a little bit different from each other. But these are all close enough that they're not statistically different from each other. So I can say that there were no sequence effects. In other words, it didn't matter which order the dogs got the food in, they always ate more chunks and lumps than anything else. And now I can show that with math, not just say, I think so. Because when you average things together, it could be that you're missing important variation. It's getting wiped out when you cut things off. You could have a really high score and a really low score, they average out to a middle score, and you don't really see that variation. But here we can really look at it and see how different things were in terms of different orders. I couldn't do this if I didn't have factorial designs, where I can have one independent variable, which is the food, and one independent variable, which is the order. So factorial designs allow us to systematically address the challenges of different types of single factor designs. They also allow us to build on existing research. So say I have a study that involves a single factor. I can add another factor or modify the factor that they used, or combine factors from multiple studies that address similar problems and use these new formations to expand our understanding of how those IVs impact behavior. It can allow me to better understand the external validity of a finding. So how far does this generalize? Is it the same for all different kinds of people, all different kinds of dogs, all different kinds of foods? Or are there limits to the effect? It also allows us to identify what we call moderating variables, variables that influence whether or not an effect occurs. So, for example, imagine an experiment where you get a bunch of people together. We're going to get a bunch of men together, and we're going to give them the opportunity to drink a beverage. Now, everybody is going to drink a beverage that they think is alcoholic. Some of them are going to have a non-alcoholic beverage, some are going to have an alcoholic beverage. And at some point, we're going to end up with half of our subjects being drunk and half of our subjects being sober. Okay? And we're going to give them the opportunity, at that point, after they've consumed some amount of alcohol, to administer electric shocks to somebody else. Not really. That wouldn't be good. But we're going to let them think they get to administer electric shocks to somebody else because they're doing something wrong. Okay. So maybe, I don't know, let's really Y chromosome this to death and say we're going to have, a lot about, maybe they're really playing Madden football. Okay, so they're going to watch other guys playing Madden football, and every time they do something wrong, they're going to shock. Okay, I'm totally making this up. So what we see is that people in the placebo group administer less shock than people in the drunk group. So you might say, hey, drunk men are more aggressive than sober men. Okay. When men are drunk, they're more likely to give harder electronic shocks to other men. All right? But that's just one factor, right? That's one IV. We've got a placebo group and a drunk group, so there's our experimental group and our control group. just one IV, right? Either they got alcohol or they didn't. One DV, the intensity of the shock. But what happens if we add another IV? The physical body size of the subjects. So we divide the men into light men and heavy men. Now, why might I be interested in this? Well, we know that alcohol affects people of different sizes differently, right? People who are less body size, less body mass, might get drunk sooner than people who have more body mass, right? It's one of the reasons I love body mass, because it means I can drink. All right, so everything. Anyway, so it means I have to have like 6 of these a day, but okay. But let's divide it up. So we're going to have the light men and the heavy men. Okay. Now, what do you notice when you look here? So for the placebo group, was there really much difference between the light men and the heavy men and how much they shock? No. But what about the drunk group? Yeah. What do you see? What's happening with the drunk group? The heavy men are giving more intense shocks than the light men. Okay? So that suggests that alcohol affects men's aggression differently, okay? Depending on their body weight. Big men become more aggressive than smaller men when drunk. Why might that be?
More testosterone.
Maybe. What happens if you're a big guy and you get aggressive?
They know they're more likely to win.
They're more likely to win. Small guys who get aggressive get their butts kicked. So maybe there's something going on here with body size. Smaller men might be less likely to get aggressive when they're drunk, because if they're going up against a big drunk guy, they might not win. Now, of course, we know this. We're talking about broad generalizations here. There are small guys who completely kick butt and big guys who can't do a damn thing. We know that. Okay, but we're talking about generalizations here. So if we look at this, what we can see is that body weight moderates the effect of alcohol on men's aggression. And we can only see that if we look at both IVs together, right? We have to see that at this, it's not that heavy men are always more aggressive. It's that heavy men, when they drink, are more aggressive than lighter weight men when they drink. Still, it's also true that when they're drinking, everybody's more aggressive than when they're sober, even if they think that they've been drinking. So it's not just thinking that you're drinking that matters. You actually have to have the alcohol in your system to get this effect. So this is something we could only see if we looked at 2 IVs at the same time. It wouldn't show up with 1 IV. So when we talk about factorial designs, we characterize them in terms of several features. First feature is the number of independent variables in the study. So we're going to talk about 2 things. One is factorial notation, and the other is factorial design. So the number of IVs is important for the notation. Okay, we're going to talk about what goes into the notation in a second. The next part is the number of levels in each IV. So these 2 things, the number of IVs and the number of levels in each IV, those are represented in the notation. Then the types of IVs you have. Do you have between subjects IVs or within subjects IVs? Do you have manipulated IVs or subject IVs? These contribute to the type of design. Other things that contribute to the type of design. For between subject studies, did you use random assignment or matching plus random assignment? That's going to change the factorial design. And for within subject studies, was it complete or incomplete? And did you use full or partial counterbalancing? You're thinking, oh my gosh, that's stuff from like exam 2. And I'm like, yep, you never get to forget anything in this class. So if you don't remember the difference between full and partial counterbalancing or complete and incomplete designs, you don't remember those things, make sure you go back and review it because you need to know. So let me give you an example. Let's say we have a study where we're going to explore that classic home remedy. You've heard this. If you know somebody who's had too much to drink, what they need to do is drink some coffee before they try to drive, right? So they've had too much to drink, give them a couple cups of coffee, and then it should, I don't know what, cancel out, right? Because alcohol is a depressant and caffeine is a stimulant. So if the alcohol has depressed their reaction times for driving, the caffeine should improve their reaction times, and so they should be okay to drive. Or something weird like that. Okay. So imagine that you're doing an experiment where you say, okay, so we're going to have people who either have a level of alcohol, blood alcohol content where they're legally intoxicated, or they're not drinking at all. Okay, so drunk, not drunk. And then we're going to give people 400 milligrams of caffeine, or 200 milligrams of caffeine, or no caffeine. So I've got two IVs, two different beverages, or two different kinds of drugs that I'm going to give them. And now let's talk about the notation and the design. Okay. So how many IVs do I have? Two. Okay. How many levels does the first one have? Two. How many levels does the second one have? Three. Okay. So the notation for this study is a 2 by 3. Okay, that's the factorial notation. You're always going to have one number for each IV. So you have to know, we've got two IVs, that means I'm going to need two numbers. The first number is going to tell me how many levels are in the first IV. The second number is going to tell me how many levels are in the second IV. So 2 by 3. That's the factorial notation. The factorial design type is defined by other things. So do I have a between subjects variable or within subjects variable? Well, this one's between subjects because you can't be drunk and not drunk. Right? So people are going to be one or the other. Okay. It's a manipulated variable because I can randomly assign people to the drunk group or the sober group. And random assignment because unless there's some clearly stated matching variable, you assume that people are doing random assignment. There's no reason for them not to do random assignment. Then, same thing for amount of caffeine. Between subjects variable. One group's getting 400 milligrams, another group's getting 200 milligrams, another group's getting 0 milligrams. It's manipulated. I can randomly assign subjects to get one of those things. So I would call this a random groups factorial design because it has all random assignment, all between subjects. Now, just to get a sense of how many different options there are, take a look at the flow chart. So when you're trying to decide what kind of factorial design you have to think about the IVs. So if you have all between subjects IVs, like we do in this case, then first thing you ask yourself is, are the IVs manipulated variables or subject variables? If they're all manipulated, like we have in this case, then you come down here. How are the subjects assigned to different conditions? You say, oh, random assignment. Okay, random groups factorial. All right? So what you're going to learn as part of this unit is how to recognize different factorial design types. Now, we've talked about designs that are very similar to these three already. This is just random groups factorial is all between subjects, everything done with random assignment. Matched groups factorial is all between subjects and at least one variable was matched. Okay? Natural groups is all between subjects, but everything is subject variables. Okay? So these are both all manipulated variables. This one is subject variable. So we've talked about stuff like that. We've talked about things over here. Different kinds of within subjects designs. Before we've talked about complete repeated measures design, right? That's where subjects experience each condition more than once. We've talked about incomplete designs. That's where they experience each condition only once. We also talked about full counterbalancing and partial counterbalancing. Full counterbalancing is where all possible random orders of the conditions are used. Partial counterbalancing is where only a subset of the possible random orders are used. Okay? So these are very similar to the kinds of designs we've already talked about. It just so happens that now we're talking about having multiple IVs. The kinds of designs we haven't talked about yet includes things like P and E factorial. A P by E or P and E factorial. P stands for participant, E stands for environment. P and E factorials are designs where you've always got one manipulated variable and one subject variable. So if one's manipulated and one's subject, that subject variable is the P variable, that's the person variable, or the participant variable, and E is the manipulated variable. So if you get one subject variable, one manipulated variable, you've got P and E factorial. There's some other kinds of designs that we talk about if you get one between and one within subject variable. So flip it over. If they're all manipulated variables, then because you have one between and one within, we call it a mixed factorial design. As long as they're all manipulated. If you've got one manipulated variable and one subject variable, then what we want to know is the within subject variable time? Because time is a special variable that cannot be counterbalanced, right? Before and after can't be counterbalanced. You can't have some people do something after and then before. It doesn't work. So time is a special kind of variable. So we treat it like a special variable. So it actually, we talk about special kinds of designs. We talk about pre-test, post-test designs. So you can have different kinds of designs if you have one between and one within. So one of the things you're going to have to work on in this unit is being able to read summaries of studies, like we've been doing all semester. You're going to have to be able to identify the IVs. You're going to have to be able to tell whether the IVs are between or within. You're going to have to be able to tell if the IVs are manipulated or subject. You're going to have to be able to tell how many levels each IV has and identify the proper kind of design. Okay? So we don't really have a lot of formulas on this test. So one of the things you're going to want to have on your note card will be details from this chart if you don't memorize. All right. So let's go back to here. So let's try this again. Let me fix this, because it always does this. It stretches it out in a weird way. So when we talk about a 2 by 3 random groups factorial, the first number here tells us the number of levels for IV1. The second number here tells us the number of levels for IV2. And this right here is the factorial notation. This part right here tells us about the kind of IVs we have. Were they between subjects variables, within subjects variables? Did we have random assignment? Did we have matching? Did we have complete design? Did we have incomplete design? Those kind of things. Those all happen right here. That's where that part of the name comes from. And then all of the designs include the term factorial, indicating that we're talking about more than one IV. So when I ask you to give me the factorial notation and factorial design for a study, you need to give me both parts. And there will be time on the problem set. There will be a number of questions where you have to practice using this chart and working through solving problems. Okay, so let's try one. Say we're doing chunks and lumps, because it's always good to go back to what's familiar. So our first IV is breed of dog. Our second IV is type of food. I've got 3 breeds of dogs: bulldogs, greyhounds, and labradors. 3 types of food: chunks and lumps, Purina 1, and Kroger Kibble. Right? They both have 3 levels. This is between subjects because a dog can't simultaneously, can't be a bulldog now and then a greyhound and then a Labrador. It's one or the other, right? We're going to do this one within subjects. It's manipulated. This is subject variable. We're going to use ABBA counterbalancing here for this. So that makes it a complete design. So tell me, what kind of design do I have? First, give me the notation. What's the factorial notation? 3 by 3. Okay, so this is a 3 by 3. Okay, now, we've got a between subjects subject variable and a within subjects manipulated variable. Okay, so what do? Where should we look? Chart 2. Okay, we're going to go back here to chart 2 then. All right, so we have a between subjects subject variable and a within subjects manipulated variable, right? Okay, so they're not all manipulated, so we can ignore this. They're not all subjects, so we can ignore this. So we're here in the middle. All right, we've got one manipulated variable and one subject variable. Is the within subject variable time? No. What's our within subject variable? Food, right? So it's not time, so we have a P&E factorial. Okay? A 3 by 3 P&E factorial design. Make sense? Notation, design type. Both parts of information. Now, the notation part actually turns out to be kind of useful because when you look at this part right here, it's actually telling you something useful about the study. This is 3 by 3. That means that there are actually 3 times 3 different conditions in the study now. That means there are 9 different conditions in this study. Okay. And that's also true. Let's look at this. Let's go back to our drinking alcohol and caffeine. So this was a 2 by 3 design, right? 2 by 3. Well, 2 times 3 is 6. And there are 6 different conditions. So I've got the people who get no alcohol and no caffeine. That's one condition. I've got people getting no alcohol and 200 milligrams of caffeine. That's another condition. No alcohol and 400 milligrams of caffeine. That's another condition. Alcohol and no caffeine, alcohol and 200 milligrams, alcohol and 400 milligrams. So that 2 by 3 tells me how many different conditions I have in my study. How many different unique combinations of the levels of the IVs. And any one of those, or any number of those, could end up with interesting results. What we're interested in is what combinations seem to matter. What combinations do the best? What combinations do the worst? For example, in terms of the dependent variable. What combinations don't differ from each other at all? Now we've got lots, even more different things to consider with our statistics. When we do data analysis on factorial designs, we get 2 different kinds of results. The first kind of result is what we call a main effect. And main effects are what we've been looking at all semester. We just never call them main effects because we didn't have to distinguish them from anything else. But now that we do have to distinguish them from something else, we're going to give them main effects. A main effect is the effect of a single independent variable on the dependent variable. So when one independent variable has a significant influence on one dependent variable, we say that there's a main effect of that IV on the dV. When that independent variable all by itself shows significant differences in terms of the dependent variable. Because we have two independent variables in our alcohol caffeine study, we have the possibility of getting two distinct main effects. We could have a main effect of alcohol, where it matters whether you got alcohol or didn't. And that's significantly different. We could also get a main effect of caffeine, where it matters how much caffeine you got. Your behavior on the DV varied whether you got 0 milligrams, 200 milligrams, or 400 milligrams of caffeine. So there's a possibility for one main effect for each independent variable. So if you have two independent variables, it's possible for you to have two main effects. Doesn't mean you will, but it means it's possible. If there are three independent variables, you could have three main effects. If there are four independent variables, you could have four main effects. Doesn't mean you will, just means it's possible. What you want to remember is that main effects are about individual treatments. They're about individual IVs. So if you're talking about the influence of a single independent variable on the dependent variable, you're talking about a main effect. We can say there's a main effect of alcohol. We can say there's a main effect of caffeine. But as long as you're talking about one variable, you're talking about a main effect. We've been talking about main effects all semester. What's new is our ability to talk about interactions. Talking about how independent variables combine to have an effect on a DV. And one way to think about this is that an interaction occurs when one independent variable influences another independent variable. So these two variables somehow combine or interact or influence each other in a way that causes a unique response in the subject. So, for example, it could be that drinking alcohol or having alcohol in your system changes how your body responds to caffeine. Or that it could change in a way that amplifies the effect of caffeine, right? You could have a drug interaction, right, where having this particular drug in your system and then taking this particular drug makes the other drug freak out, and you have an increase of effect of one of the drugs. You could also, it could work the other way, where having the two drugs in your system at the same time results in a decrease of one of them being effective. That's what we're kind of trying to do. We're trying to change it so that, say you've already got this alcohol in your system, then we have people dump caffeine in, hoping that what it's going to do is change the way the alcohol is affecting your body, right? We're trying to get it to cancel out the depressant effects of the alcohol by amping you up with the stimulant. Right? The whole reason people do drink coffee or Red Bull or whatever, trying to get sobered up so they can drive home from the party, is they're trying to cause a drug interaction. They're trying to make the power of one cancel out the power of the other, so that the person will be able to get home. So what you want to remember about interactions is that they are about combinations of treatments. When you talk about an interaction, there's always more than one IV involved. So you talk about the interaction of alcohol and caffeine, or the interaction of breed and food type, or the interaction of road conditions and driving experience. It's always about a combination of things. So interactions always reflect combinations. So let's look at some data, just to see how this pans out a little bit. So we're talking about that same study. I've got the IV of alcohol over here, alcohol and no alcohol. I've got the IV of caffeine across the top. Now we know it's a 2 by 3 design. That means there are 6 different conditions, right? 2 times 3 is 6. So this condition right here is the people who were drunk and got no coffee. These are the people who were drunk and got 1 cup of coffee. These are the people who were drunk and got 2 cups of coffee. Make sense? Okay. All different groups of people. These are the people who were sober and got no coffee. Sober, 1 cup of coffee. Sober, 2 cups of coffee. And then the dependent variable was their performance in a driving simulator to see how well they drive under those conditions. Because we're not actually going to send people out on the road once we've gotten them drunk. That would not be responsible. And these values show their average response times to various obstacles. So higher numbers mean that they were slower to respond. Smaller numbers mean they were faster to respond. Okay? You with me? Everything make sense so far? All right. So if we want to figure out if there's a main effect of alcohol, okay, a main effect of that first IV, whether they were drunk or not, okay, here's what we do. We're going to take a grand average and we're going to compare the 2 conditions. So if I take an average of these 3 numbers, that gives me 650. Okay, if I add these 3 numbers together and divide by 3, then it's 650. If I take the average of the no alcohol numbers, that's 600. So a main effect, we would have a main effect if the difference between these 2 numbers is statistically significant. Okay, that would be a main effect of alcohol. So if we were doing this just by itself, if all we were looking at was alcohol, we'd be running a t-test here. We'd be comparing the mean for people who had alcohol to the mean for people who had no alcohol. And we look to see if there was statistically significant. And if the difference was statistically significant, we'd say, yep, we've got a main effect of alcohol. What we can see here is that there's an observed difference of 50 milliseconds. All that matters now is what's a critical difference. We don't know immediately, because we don't know about degrees of freedom and all that other stuff, what a critical difference might be. But if I told you that the critical difference was 25 milliseconds, then what would you say? If the critical difference was 25 milliseconds, and I've got an observed difference of 50 milliseconds, does alcohol matter? Yes. Because my observed difference is 50 milliseconds, and all I need to have a statistically significant effect is 25 milliseconds. So you can think of this kind of like doing one of those post hoc tests, right? Where all you're looking to see is the number bigger than the one that's the critical value? So this is how we would consider, just in a very superficial way, the main effect of alcohol. And if this was all we were doing, we'd run a t-test. But that's not all we're doing. We're also doing caffeine. So if I wanted to figure out if there was a main effect of caffeine, then I would take an average of the 0 milligram people, and an average for the 200 milligram people, and an average for the 400 milligram people, and I would look at these differences. Now, I've got a difference of 25 here, a difference of 25 here, and a difference of 50 here. So if I have, it depends on what my critical difference is. If I said the critical difference is 25, what if I said the critical difference, we'll make it a little more straightforward. What if I said the critical difference is 30? Do I have a main effect of caffeine? Think about doing Tukey tests. If I said the critical difference was 30, do I have a main effect of caffeine? Look at the numbers. Think about all the possible differences. What do you think? Are any of the pairs more than 30 apart? Yes. 650 and 600 are 50 apart. Okay. So that means that we would have a main effect of caffeine, and if we did a Tukey test on it, we'd find that it was this comparison that was driving the effect. Okay. So if any of the differences, any of the pairs, are more different than whatever critical difference I give you, that means we have a main effect of that variable. Now, when we do this kind of analysis, we would be doing an F-test here, right? Because we've got 3 levels. It turns out that whenever we do factorial analysis, we do ANOVA. So even though the first one had 2 levels and this one has 3, we would be doing F-tests on everything. So we would do an F-test for alcohol, we would do an F-test for caffeine, and then we would do a third F-test for the combination of alcohol and caffeine. Now let me tell you, nobody hand calculates 3 F-tests. Nobody. If you're in a lab where they're doing analysis of variance like this on factorial designs, they're going to have you plug data into a program like SAS or SPSS and run that analysis. So in this class, I'm not going to make, I have taught people how to hand calculate the factorial ANOVA just like I taught you guys how to do one-way ANOVA. But that's not what's really important about this. I know you guys can plug and chug ANOVA. As long as you've got the formulas in the boxes, you got this. That's not really a concern. What's more important is that you understand the main effects in the interactions and that you're able to do things like read tables of information that summarize the effects of these kinds of analyses, and that you're able to interpret graphs that show the different kinds of effects. So that's really what we're going to focus on. We're going to do a little bit of discussion about analysis, but not nearly like what we've done in the past. Very limited. Mostly it's going to be finding new applications for the stuff you already know how to do about ANOVA. But this is how we would do something like main effects. Now what about interactions? This is the new thing. When we talked about main effects, we're basically getting averages and comparing the averages. Okay? Adding, averaging. But now we have an interaction. How do I do an interaction? Well, the simple way to do an interaction is something like this. We call it the subtraction method. And what you do is you subtract one level of the table from another level of the table. So in this case, it just so happens that the no alcohol scores are more consistently low, and the alcohol scores are more consistently high. So the obvious way to do it, to keep the math simple in your head, is to subtract the no alcohol score from the alcohol score. So I'm going to do it the easy way with just 2 numbers, because subtracting 3 numbers gets messy. So let's just say take 675 minus 625, and the difference is 50. 650 minus 600, difference is 50. 625 and 575, the difference is 50. Okay, so these are my differences. Now I look to see if any of these are different from each other. What do you see? Are there any differences there? No. None. 0. That tells me there is absolutely no interaction here. These 2 variables aren't affecting each other at all. All the differences we see in the data can be explained in terms of what coffee does, or what caffeine does, or what alcohol does. But it's not that the 2 of them are doing anything together of any interest whatsoever. Right? So the magical cocktail of coffee plus scotch doesn't actually help you perform better on the road. There's no difference. It makes absolutely no difference. So there's no interaction of alcohol and caffeine. What does this look like on a graph? Well, we have to be able to look at graphs and see these phenomena, because in a research paper, they're going to, very often when it comes to factorial designs, present the data to you in graph form. So what we're going to do all next class period is talk about how to read graphs, bar graphs and line graphs, so that you can spot possible main effects, possible interactions in the graph itself. So here we'll just start off. Say you're looking at a line graph. If you want to know whether there's a main effect of the variable on the x-axis, what you want to look for is the slope of the lines. So look at these lines. They're not flat. The closer they get to flat, the less likely you are to have a main effect of whatever's on that x-axis. Because the closer they get to flat, the more similar they are, right? But the more the lines tilt up, or like that, the more slope you have, then the more likely you are to have a main effect. So because these lines are sloping, that suggests we have a possible main effect of caffeine. Just depends on how much slope they need to have to be significant. If we want to know whether there's a main effect of the IV in the legend, we pay attention to how far apart the lines are. If the lines are really close together, there's no main effect. If the further apart the lines get, the more likely a main effect of that variable is to be occurring. Lines that are really far apart, that means there's a really big difference between the two levels of that IV, probably you have a main effect. So the further apart they are, the more likely you are to have a main effect. So these lines are pretty far apart, so we've got a possible main effect of alcohol. What matters is how far apart do they need to be for the effect to be significant. If you want to know whether there's an interaction, we pay attention to whether or not the lines are moving towards each other or whether they actually intersect. To the extent that the lines are not parallel, you have an interaction. Now if the lines touch, or if the line, if they totally intersect, you get something that crosses over like that, you definitely have an interaction, no question whatsoever. But the closer the lines get to each other, the more likely you are to have an interaction, just in visual terms. Here you can see the lines are parallel. That means we have no chance whatsoever for an interaction. Those lines are never going to run into each other anywhere in space, because they're parallel. So no intersection means no interaction, right? Or no potential for one. No potential for an intersection, no potential for an interaction. To the extent that an intersection could occur somewhere close by, or that it actually does occur on the graph, you have potential for an actual interaction. So here's some different data. I would like you now to try. First thing I want you to try is to figure out whether we have a main effect of alcohol. Okay. So what I want you to do is the math to tell me first for main effect of alcohol. That means you need to calculate a grand average for the alcohol and a grand average for no alcohol. So go ahead and do that. Put this up so I can write on the board. Go really high tech, mixed media. Okay, so what is my grand average for alcohol? 650? Okay, and now what about no alcohol? 600? 610 plus 600 plus 590 divided by 3? 600. So, my observed difference is 50. That's my observed difference. So if my critical difference is smaller than that, I've got a main effect. If my critical difference is larger than that, I don't have a main effect. Make sense? Now, What about caffeine? Okay, let's say we're going to do it for caffeine. I need to take an average for 0 milligrams. What's the average for 0 milligrams? 650? And what's the average for 200 milligrams? 625? And what about the average for 400 milligrams? 600. Okay, so what do I have? I have a difference of 25, another difference of 25, and a difference here of 50. Okay, so just like last time, depending on what my critical difference is, either none of them are different, these two are different, or they're all different from each other. If I have a critical difference that's 30, then the only significant difference here is between these two, but I do have a main effect of caffeine. Okay, what about the interaction? Now I'm going to do that subtraction thing, where I subtract one level from another. Easiest way to do it, again, is to subtract no alcohol from alcohol. So what's 690 minus 610? What about 650 minus 600? 50. Okay. And what about 610 minus 590? 20. Okay, so now these numbers are different. So I see that between these two conditions, I've got a difference of 60. Between these two conditions, a difference of 30. And between these two conditions, a difference of 30. So if I have a critical difference of 50 now, that means I have an interaction, okay, for the first time. So as long as any of those pairs has a difference that's bigger than whatever critical difference I give you, you have an interaction. So we've got a possible main effect of alcohol, possible main effect of caffeine, and a possible interaction. All depends on what the critical value is for that particular set of data. So let's look at what this would look like on a graph now. When you have two main effects and an interaction, it looks a little bit different. You remember last time I told you that if we're looking at whether or not there is an effect of caffeine, or effect of whatever's down here on the x-axis, we're going to look at the slope of the line. Well, that bottom line's pretty close to flat, but the top line's got a lot more slope. So, or a lot more extreme slope. So, looks like we might have a main effect. Ash told you that when you're talking about whatever IV is there on the legend, you look to see how far apart the bars are, how far apart the lines are. And here you can see, well, they're not very far apart here, they're definitely very far apart there. And that suggests that you might have that main effect of alcohol. But what makes this graph really different from the one we saw before is that now, rather than the lines being parallel, they're very clearly moving towards each other. And we can imagine somewhere in space, not very far out here, that they might actually converge if we went out to 600 milligrams of coffee. We might actually see a convergence that way. So the fact that these lines are not parallel makes it very clear that we have an interaction. What this graph also makes very clear is that in the presence of an interaction, the cues that we use to tell whether there's a main effect of the x-axis variable or the legend variable get skewed. The cues we use are skewed. Alliteration is a good thing. Okay? In the presence of an interaction, the cues get skewed. And what that means is it's possible that in the presence of an interaction, something that is not a main effect could look like one. because the interaction makes it look like one, because it skews the cues. So in the presence of an interaction, we don't worry too much about the main effects, because we don't know anymore if they're real. It's possible that the main effects are actually artifacts of the interaction. It's just making it look like there are main effects because of the way the interaction is happening. So whenever we have a factorial design and we're looking at the data, we always want to know first if there's an interaction. And if there's an interaction, we have to take the main effects with a grain of salt, because they could be artifacts of the interaction. They could be false main effects. They could be exaggerated because of the presence of the interaction, or a main effect that's actually there could be hidden because the interaction covers it up. So it's hard for us to trust main effects in the presence of the interaction. The important thing here in this is that there's an interaction. Do we have main effects? Mathematically speaking, we certainly could, but we want to be very gentle in interpreting those or generalizing those. If we really want to know about the effects of individual treatments separate from one another, we need to study them separately. And that's why single factor designs still happen. But what we're really curious about when we combine factors is what happens with the combination. And here we got an interaction. That's what's really interesting. So when analyzing data like this, our first priority is always determining whether or not we have an interaction. Interactions can obscure and distort main effects, making them hard to interpret. So it's really only meaningful to interpret main effects when there's no interaction. If you've got that interaction, you want to talk about the interaction, figure out what it means, because that's what's the really compelling finding. The other stuff is kind of maybe could be meaningful, could not be meaningful, we don't know for sure, because of the potential for distortion. Another way to think about it is, in the presence of an interaction, you're at a higher risk of committing type 1 or type 2 error with regard to the main effects. And since you want to avoid committing errors, you just say, we don't know. This is kind of what it looks like, but if we really wanted to know what happens with this in this particular IV by itself, we'll study it by itself. In the presence of this other IV, this is what it does, and that's what's interesting. Now, when you're doing a factorial design and looking at the data, any combination of main effects and interactions are possible. So if I had two IVs, I can have no main effects, one main effect, two main effects. I can have no interaction or an interaction. I can have any combination, right? So I can have main effect, no interaction. Two main effects, no interaction. One main effect, one interaction. No main effects, an interaction, right? It doesn't matter. Any combination is possible. So you don't know, because you have one effect, whether you have the others. You have to do the math for all of it. So when we start doing math, like the kind of math we did today on these, you have to do the math for all three things. The main effect of IV1, main effect of IV2, and for the interaction of IV1 and IV2. You have to do all the tests because any combination is possible. So let me ask you a question. How many main effects and interactions could you have if a study had 3 IVs? So you've got IV1, IV2, and IV3. How many main effects can you have? And why? How many main effects can you possibly have?
3.
Okay, why?
Because there's 3 IVs.
That's right. So you have the possibility of one main effect. IV1 could affect the DV by itself. IV2 could affect the DV by itself. IV3 could affect the DV by itself. Okay? Exactly right. Now, how many interactions can you have? Now people are quiet. How many? 3. Okay, what would the interactions be?
1 and 2, 2 and 3, and 1 and 3.
Okay, so there's IV1 times IV2, IV1 times IV3, IV2 times IV3. Okay.
Can it be all the way up to 2 and 3?
That's right, you got it. Hey, my students are so smart. So these here are called two-way interactions. And this one here is called a three-way interaction. So if you have 3 IVs, you can have 4 possible interactions. So the more IVs you add, the more analyses you have to do. It starts to get crazy. For my dissertation, I did experiments. I did multiple experiments, and they all had 4 independent variables working simultaneously. The interactions were insane. They were really fun to try and analyze when you're a nerd like me, but I had a lot of interactions. So we're always interested in interactions. So people love to run studies with 3, 4 IVs and try to figure out how they work together, because that's how real life is, right? Real life has lots of different factors impacting every decision and every behavior. So we try and build on studies gradually, trying to get a sense of what affects what interacts with what doesn't have anything to do with what else. That's what these kind of designs let us do. So the answer here is you would have 3 main effects, 1 for each IV, and you have a possibility for 4 different interactions. 3 interactions that are two-way, and 1 interaction that's three-way. All right. That's what I have to talk about today. Next time, we're going to talk about reading graphs, main effects and interactions. We're going to get really, really good at it.